So here we go with another video for calculus. So this video is starting kind of the last topic that we'll see, the major topic for this course, and this will kind of lead you if you're going to take Survey of Calculus 2 or Calculus 2. This will lead into the major topic that is in Calculus 2, which is integration. But we're going to spend the last few sections going over this idea, and it starts with the idea of the antiderivative. And so the antiderivative is just the opposite of the derivative, of course. So essentially, if you have a function that is the derivative of some function, then that derivative is called, well, the function that the original function, little f of x, this capital F of x is the antiderivative of the little f of x. So basically, instead of having a function and taking the derivative of it, we're going to go backwards and we're going to start with a function and find what function would that original function be the derivative of. So to give you an example here, find the antiderivative of 8x to the 7th. Now, this looks like a power function, and it is a power function. So how did we find the derivative of a power function? So if you remember, if you have x to the n and you want to take the derivative of it, then you bring the n down, n times x, and then you subtract 1 from the exponent. So the derivative of x to the n is n times x to the n minus 1. Well, we have a very similar form here to this, and we just need to match up what we have. So we need x to the n. Well, n apparently is going to be 8. So the antiderivative, so if f, we'll call this f, capital F prime of x is 8x to the 7th. So using this form, f of x is 8x to the 7th, so we'll call capital F prime of x 8x to the 7th. Well, it looks like n is going to be 8, so that tells us that, actually we should write capital F of x is x to the 8th. And so what happens if we take the derivative of this, we end up with the function that we started with. So we found the antiderivative. Now this is a little bit clunky in the way that we did it. It's not really so much a guessing game. Of course, we're going to learn formulas and techniques, and we'll get into that a little bit in this course in the next few sections. And then if you take Calculus 2, you spend the first several weeks doing integration, finding antiderivatives. Now, one thing to pay attention to with antiderivatives, imagine if, so I guess capital F of x equals x to the 8th has a derivative of 8x to the 7th. What if we have x to the 8th plus 3? Well, it still has the same derivative. So in other words, there can be more than one answer to what is the antiderivative of this function. So the way we can talk about this, because you could also say capital F of x is x to the 8th plus 9, or capital F of x is x to the 8th minus 7, or whatever number you want, because the derivative of the constant is just going to be 0. The derivative of x to the 8th is 8x to the 7th. So generally speaking, we could say, so a general antiderivative would be capital F of x equals x to the 8th plus c, where c is just any constant, any real number, because the derivative of a constant, of course, is 0. Now, if capital F of x and capital G of x are both antiderivatives of this function, then there is a constant c, so that capital F of x minus capital G of x equals c. Now, that's just really illustrating the fact that we could use any constant here. So if we call, let's say this one is capital F of x, and let's say capital G of x is x to the 8th plus 3. Well, if you, both of these, take the derivative of either one of these, you get 8x to the 7th. if you subtract f of x minus g of x, you would end up with x to the eighth minus 7 minus x to the eighth plus 3, which would just be negative 10. So it'll always be a constant. And it's because you could really have any constant here. So you could attach any constant after the main part of the function. All right, so the next thing is what's called the indefinite integral. So antiderivative and integral are very similar ideas. Let's see, don't know what's going on. Whoops. All right, let's try this again. No. So if f, well, sorry, a little bit of lag there, I guess. If capital F prime of x equals f of x, then this symbol is an integral. And an integral is just a way of symbolically talking about an antiderivative. So you have the integral of f of x, and now this tells you which variable you're integrating with. So if you go on to say calculus 3, which is multivariable calculus, you get into functions of x and y, or functions of x, y, and z. So you have multiple variables, not just an x. And so you may see f of x, y, dy, which means you're integrating over the y instead of the x. But we're just working with x, or whatever the one variable is. And so this is just, we need to find the antiderivative. Whenever you see that symbol, find the antiderivative of that function. So let's see some rules here. So first we'll start off with the power rule. Of course, power rule is probably the most basic one, most fundamental. And so for any real number n not equal to negative 1, and we'll see why that is in a minute, the integral, or the antiderivative of x to the n dx. Now you're doing the opposite of how you found the derivative, right? So we need to add 1 to the exponent instead of subtract 1. And then instead of multiplying by that exponent, we're going to divide by that exponent. And then we're going to put this plus c. So anytime you find an indefinite integral or a general antiderivative, you always need to add a plus c, because again, when you take the derivative of this function, you should end up with x to the n. And so it doesn't really matter what the c is. The c will just be a constant. When you take the derivative, it goes away. So let's see how this works with an example. I don't know why my computer is being very, very finicky here. So let's integrate 1 over t to the fourth dt. Now, if you were taking the derivative, probably you'd write this with the t in the numerator, and we're going to do the same thing because it's just easier to see what we need to do. So let's write this as t to the negative fourth dt. Again, the dt isn't really, it's not really doing much as far as how we need to integrate this function. It just tells us that we are integrating. So the dt goes with the integral sign. So we're just going to follow this formula. So n is negative 4. So we need to add 1. So that would make it t to the negative 3. And then we divide by this new exponent plus c. And if we want to rewrite this, we could write negative 1 over 3t cubed plus c. And that would be our answer. Probably either one would be fine, though. All right. Now, if you remember from limits and derivatives, we have constant rule, multiple rules. We have sum and difference rules. I don't know what's going on with this. All right. Let's see if we can scroll this. Okay. So if all indicated integrals exist, then as you can imagine, we can just pull the constant k outside the integral and just integrate the function as normal. If we have a sum or a difference, we can split the integral and write the integral of f of x dx plus or minus, as the case may be, the integral of g of x dx. So just like you would expect with derivatives, you can split the derivative and take it term by term. You can pull a constant out, and you can do the same thing with these integrals. So let's integrate this polynomial, 6x squared plus 8x minus 9. I don't really need to rewrite this. It's already in a good form. So we have 6x, add 1 to the exponent, so that'll be a 3, and then we divide by the new exponent. Plus 8, add 1 to the exponent, so we have x to the first, so let's make that an x squared, and divide by the new exponent. Now, what's the antiderivative of a constant? The antiderivative of a constant would be a linear function, so 9x, because if you take the derivative of negative 9x, you get negative 9. So kind of the good thing about all these, any of these antiderivatives or integrals, when you get your answer, you can take the derivative of this and see if you get back to the original function. So it's very easy to check your answers. Now, let's just simplify this. We get 2x cubed plus 4x squared minus 9x plus c, where c is any constant. And you can check if you take the derivative of this, that one won't take but a second, you can see that we'll end up back where we started. All right, so let's look at another one. So this one looks a little bit more complicated. But when you just have one term in the denominator, you can divide that into each term in the numerator. So let's do that. So we're going to divide square root of x into x cubed. So we'll subtract the exponents 3 minus 1/2. So that gives us x to the 5/2. And then 2 over square root of x, let's write that as 2x to the negative 1/2 dx. And so now some of these, like this one, you got to get used to adding fractions maybe, or at least adding 1 to a fraction. So this is still a power function, and so let's add 1 to the exponent. So we get x to the 7/2 over the new exponent, which is 7/2. Minus 2x, add 1 to the exponent. So negative 1/2 plus 1 is going to be a positive 1/2, divided by a positive 1/2 plus c. And then let's simplify this. So x to the 7/2 over 7/2, that'll give us a 2/7 x to the 7/2 minus 2 divided by 1/2 is going to be 4. And we could write x to the 1/2 for square root of x either way. And there is our answer. Okay, and again, if you want to take the derivative of this, you can see that you'll get back to this, and then you can change this back into this if you like, but at least take the derivative and see if you can get back to this. All right, now indefinite integrals of exponential functions. So the derivative of e to the x is e to the x, so it stands to reason that the antiderivative of e to the x is e to the x plus c. Here, the integral of e to the kx, now we're going to have e to the kx, and instead of multiplying by that derivative, we have to divide by that derivative, plus c. And then if we have exponential function where it's not just e, I think I need to wait for this to catch up. I don't know why my computer is running so slow. I have too many things open. We have a to the x over ln of a plus c. And then for a to the kx, we have a to the kx over k ln of a plus c. All right. Now, so remember when we did the power rule, I won't scroll back up since my computer's acting not good today. Remember we said x to the n, except when n is negative 1. Now, why is that? Because if we add 1 to this, if we follow that power rule formula, and we add 1 to this, now it becomes 0. So it's x to the 0 divided by 0, which doesn't work. But do you remember, and maybe think quickly to yourself, what function have we seen whose derivative is 1 over x? And if you remember that, that is ln of x. Now we need to put absolute value here because here x could be anything, but if we're taking the ln, it needs to be a positive number. So, so there's that. And in the next video, I will make sure that all my other tabs are closed. I think that may be why this is doing so poorly. Okay, so let's look at this one. This one combines a couple of ones. So, of course, we can look at this, each one separately and integrate. So 3 over x, of course, we can pull that out, that 3 out. And the integral of 1 over x is just ln of x, so we can write this as 3 ln of x. Integral of e to the negative 3x, we're going to divide by that negative 3. And then add a plus c. And I think we'll just leave it there. We could write minus 1/3 e to the negative 3x if we want, but I think that's fine. All right, now this last one. Find an equation of the curve whose tangent line has a slope of this and passes through the point 1, negative 2. So basically when you see this, now we need to figure out what the c is after we take the antiderivative. So let's figure out what f is. We know what f prime is. Let's figure out what f is. So we're going to add 1 to the exponent, which would make it 3/2, and divide by that new exponent, 3/2, plus the antiderivative of 4 is 4x. And if you like, I mean, this is a power function, if you like, 4x to the 0. So now we add 1 to the exponent and divide by that 1, the new exponent. So it gives us 4x. But you can also just remember, if you have a constant, just put an x next to it. That's the antiderivative. Plus c. So let's write this. 3 divided by 3/2 is 2. X to the 3/2 plus 4x plus c. So now it passes through this point. So we're going to plug that in. So y is negative 2. 2 times 1 to the 3/2 plus 4 times 1 plus c. So that gives us negative 2 equals 2 plus 4 plus c. So that tells us that c will be negative 8, looks like. So our function is f of x equals 2x to the 3/2 plus 4x minus 8. And that is our function. We can check this. It passes through this point 1, negative 2. So if you plug in 1, you get 2 plus 4 minus 8, which would be negative 2. And then we take the derivative of this, and we should get 3x to the 1/2 plus 4. So it satisfies both of these. Okay, so kind of like what you had to do with derivatives, where you got to practice these a little bit and get used to doing these. It takes a little bit of practice with these, not because the formulas are difficult, but because you have to kind of get used to thinking backwards and doing the opposite of what you're doing with the derivatives. But we're going to see more examples and get more practice as we go along through the next few sections.